the starter. We have the fuel pump. Horn. We have a power window motor, which goes in both directions. And then, of course, we have lights. The buttons are actually programmable to be latching, to be momentary, or to be flashing. Let me give you an example. Let's turn it on, and you can see that these lights are on all the time. Now let's imagine that these are the front turn signals on a car, and these are the rear turn signals on a car. And we want them to flash instead of just being on all the time. So let's turn them off, and then we're going to program them to actually be flashers instead of just parking lights. So this is red right now. We're going to switch it to be blue, and then we'll click the ones that we want to flash and turn the thing off again. Now when we turn this switch back on again, these are going to be turn signals instead of parking lights. Let's try it out. So we've got right turn signals, and then we've got left turn signals. And then, of course, if you wanted hazards, you could just turn them all on at once. Now, if you wanted to be parking lights again, all you do is hold this button down. This is the red section. We go to the blue section. We'll uncheck those and turn it back off. And now when we turn it on, we just have solid lights again. Now we can do the same thing for latching versus momentary switches too. So as you may recall, the power window motor is a momentary switch, so it only works when I'm pushing the button. But if we wanted to switch that so we can turn it on and have it stay on, we can do that. So we'll hold this down until it flashes red, and then we'll turn off these ones, because those are the switches that go to the power window motor, and then we'll turn it off again. Now watch this. And we can do the same for the other side. And now we'll swap them back again. So we'll hold this down, it changes to red flashing, we turn these ones back on, and we turn it off. Later in the video, I might even wire up an electric fan or a door lock actuator, just to make things a little more interesting. Now, the company that sent this to me is called CoLight, and this is called a 12-gang switch or a 12-button switch. Now, it comes with, obviously, the switch itself, a whole bunch of wire, which is disconnectable, which is kind of nice. Then it comes with the fuse panel, and the wires, and the circuit breaker. And the circuit breaker has a nice cover that goes over it to protect it from, getting touched by things. And then, of course, this has a nice cover that goes over it as well, which has spots to hold extra fuses. It also comes with stickers for all of your buttons, so you don't have any confusion when you're trying to turn things on and off. It does also come with instructions, and in the instructions it says the max current is 80 amps, which it also says right here, and then it actually comes with a 100 amp circuit breaker, which is a little bit strange. I would have expected an 80 amp, assuming that is its real limit. Now, when you're actually hooking up all of your circuits to this, you want to make sure that when all of the circuits are turned on, it is not going to exceed the 80 amp limit that this fuse panel has. Each terminal here has a different fuse rating, so you can see this one's 30, 30, 20, 15, 10, and 10, and it's the same thing on this side. So you'll actually end up with, 4 30 amp terminals, 2 20 amps, 2 15s, and then 4 10s. Now there's one thing that you really should know about this fuse panel, and that is that it is a negative trigger fuse panel. So that means that it sends power out all the time, even when the component is turned off, and it turns on and off the negative wire. So that means that you may have to wire things a little differently on your vehicle, depending on what kind of component you're adding to this fuse panel. And when we hook up a starter to this a little bit later in the video, that's why we're going to use a relay to convert the negative trigger to be a positive trigger. Now the switch itself has some pretty cool features too. When you turn it on, there's obviously a whole bunch of colors that you can match to your interior of your vehicle. And then if you want some other fun features, you can hold this button down and you'll see that it'll actually fade from one color to the next. And then if you hold it down again, it'll actually flip from one color to the next, which, makes things a little bit more fun on the inside of your car. Now, as you saw in the video, this control panel can actually be a latching switch, like this, where it latches to one side or the other and is on or it is off. Or it can be a momentary switch, like this one is, where you turn it on and as soon as you let go, it turns itself off. Or it could be a flasher. So this is a turn signal flasher, and when you send power into it, it sends power out in a flashing mode, which you saw when we did the turn signals on this. So the starter would be an example of a momentary switch, the fuel pump would be a latching switch, and then the turn signals would be the flashing switch. And all three are able to be programmed into this one switch panel. Now I wanted to give you a close-up of this so you have a good understanding of what this fuse box looked like up close at the very beginning of this video so that it makes sense as we go deeper into the video and we actually wire some stuff up. So you can see there's 6 fuses on this side and then 6 fuses on that side. And then each fuse has 2 terminals. So we got a negative and a positive and a negative and a positive and a negative and a positive, and it goes all the way down. And then each fuse has a rating here. So 10, 10, 15, 20, 30, 30. And each one of these circuits can't go above that. So even if you put a 30 amp fuse in this, you'd actually burn it out because this circuit is not meant for any more than 10 amps. But this one over here is meant for 30 amps, so it can do up to 30 amps. That means you can put a 5 amp in here, but you can't put a 40 amp in here, because you can always go down in fuse sizes, but you can't go up in fuse sizes. And then of course we have the large ground wire, which grounds the whole thing, and then we have power coming in from this circuit breaker, which is a 100 amp circuit breaker, and this obviously breaks the circuit, so now this wire is no longer connected to this wire. But you can easily reset it by flicking that switch, or you could obviously break it again, and then you wouldn't have any connection. And then here's a close-up of the actual switch panel. It feels like a pretty sturdy product. I think it would last a while, although I've only used it on my workbench here. And then, of course, we have all the stickers. Here you can see what kind of stickers are included. And then I'm sure if you really wanted to get crafty, you could make your own stickers and then apply them to the switchboard. Now, many people buying this switch panel might use it to hook up a whole bunch of aftermarket lights on an off-road vehicle so they can see at night. So I'm going to start off by just plugging in some lights so that you can see the very basic purpose of this switch before we get into the really cool stuff. So I just grabbed a couple 194 light bulbs to plug into this so that I can show you how it's wired. It's super easy to wire. These 194s could be replaced by a big LED light bar and it would be wired exactly the same way. You just basically plug in the positives into the positive terminal, the negative into the negative terminal, and the lights turn on. It couldn't be any simpler to do. Anybody could do this. But when I first got this switch, I was thinking, you know what? You could probably hook this up to some turn signals on a car, and they wouldn't flash quite as fast as a regular turn signal flasher would, but, you know, it might be good enough for a race car or an off-road vehicle or something like that. So what we're going to do now is we're going to turn these parking lights, or, you know, whatever you want to call these, into turn signals. And the way that we're going to do that is we push this and hold it down, and now it's going to flash red. We're going to click it again and it's going to flash blue, and we are going to click both the buttons that control these circuits and then turn it off again. So now when we turn it on and we turn on one of these, it starts to flash like a turn signal does. Now you'll see it's a little bit slower than a regular turn signal, and then of course you can do the same with the other side, and it's good enough to, you know, get you down the road. And then of course if you want hazards, you just turn them all on at once and you essentially have hazard lights on your vehicle. Now, these bulbs are 194s and they don't draw a lot of amperage, and you'll see that they are actually plugged into a 10 amp fuse, and on this side a 30 amp fuse. And that is just way too much amperage for these things to ever draw. So what I could actually do is I could actually replace the 10 amp with a 5 amp, because I know that 194 bulbs are never going to draw more than 5 amps. And I'll replace this 30 with a 5 amp. And that actually just allows the whole thing to be a little safer, because I know that these light bulbs are never going to draw anywhere near, you know, the 30 and the 10 that were in here before. So let's see if they still work. They obviously do, and that's because they just don't draw 5 amps. They're probably drawing about half an amp if I was to guess, probably even less than that. Now, if you hook up lights to your vehicle, what you want to do is actually look at the wattage or the amperage of the light, whatever you happen to have, and you'll want to use your fuse size appropriately. But one thing you never ever want to do is go over the fuse size that's written on the side of here, because each one of these terminals can handle up to a certain size, but not more than that size. So you can always downsize a fuse, but you can never upsize a fuse from what's written on the terminals here. You'll also see that I have 2 bulbs going into one terminal on each side, and that's just a simple way of connecting both lights together so they have the same exact functionality. As long as your amperage rating is below the rating that's on this sticker right here on each side, then you're totally safe to do that. Obviously, you want to make sure your wires are in the terminal nice and safe and tight, because you don't want to have any kind of loose connections. But as long as it's in there tight and it's under the fuse size limit, you're good to go. Now, a horn is pretty much the most easy circuit you could ever build on a car. It really just needs a power and a ground, and a lot of times a horn will just need a power wire or just need a ground wire, depending on the type of horn you have. In this case, we are going to send both wires from the horn back to this fuse box. One will go to positive, one will go to negative. It doesn't even matter which one on this horn. Sometimes it does on your horn. You'll have to check your own horn to see what type of horn you have, but in this one it doesn't actually matter, so you can plug it into either one, and then when we turn it on, you'll see that we obviously honk the horn. Now right now it is going into a 10 amp circuit on the fuse panel, but this horn doesn't take 10 amps or anywhere near it. So I can actually remove this 10 amp fuse and we'll put a 5 amp in its place. I might even be able to go down to 2.5 amp if I had one, but in this case I don't have a 2.5, so I'm going to go with a 5, and we'll see. It still works totally fine. You always want to go with the lowest amp fuse that your circuit needs. You never want to go too big on a fuse, because then you may overload your wires, or you're basically just introducing more risk to your whole circuit. The power window motor, as you can see, I have the part number here. I think it's a Dorman brand power window motor. It draws 13 amps. So we have to make sure the wires connected to it are able to handle 13 amps, and it's also connected to a 13 amp or more trigger wire over here on the actual fuse panel. Now the power window motor is controlled with these 2 buttons right here. And you can see you need one button for it to go one direction and another button for it to go the other direction. Now to make a power window motor work in reverse, well, in both directions, you have to actually reverse the polarity on the wires. So you might think that red is always positive and black is always negative, but on a window motor, it actually is reversed when you want it to go the other direction, and power is actually going on the black wire and ground is on the red wire. And the way that we're actually able to do that with this fuse panel and this switch is to use a couple of relays. Now these both are 5-pin Bosch style relays, which look like this when they're not plugged in, and you'll see they have 5 pins on the bottom. Each one is numbered, so the top pin is pin 87, the bottom pin is pin 30, the left pin is pin 86, the right one's 85, and the one in the center is pin 87A. Up here in the corner, you'll notice that I have wire colors that go with those pins, so you know which color goes with which pin on the relay. Now to make something like this work, we actually need to wire it to 2 different circuits on this fuse panel. And these 2 circuits that I'm using, one of them is 15 amps and one of them is 20 amps. But you can see that the window motor is a 13 amp window motor, but right now we have it hooked up to a 20 amp terminal. Now we don't need 20 amps, we need at least 13. So what I'm going to do is I'm actually going to swap out this 20 amp fuse for a 15 amp fuse. You can always downsize it, but you can't upsize it. So now both of these terminals are able to do 15 amps safely to power up our window motor. Now there are tons of ways to wire all kinds of circuits in a car. This is just one option, and it works well if you're using this CoLight switchboard. So let's get into the wiring. Now the blue wires coming out of these relays are pin 30, and you hook up one to the black wire of the window motor and one to the red wire on the window motor. The black wires coming out of the relays are both grounds. So you want to hook up the ground to the negative on this fuse box, and then the other ground to another circuit on the fuse box of the ground side. And then we'll take both pin 87, the yellow wires, and we'll connect them to one of these fuses, and then we'll take both white pin 86s, connect those together into the other positive. The last terminal that we have to hook up is pin 87A, which is the red wires, and those go to ground. You'll see them connected together right here, and then they come over and they hook up to this ground terminal right here. Now, I do have another more in-depth window motor video, which gets more into the details of it, which I will link right down here in the description. But for this video, I'll go over it quickly so you have some understanding of how it works, and then if you want to do 2 window motors or 4 window motors with one of these switches, you'll be able to do so. As you may recall, both of these powers are powered up all the time. And this fuse panel controls the negative triggers. So right now, both whites and both yellows have power right now. And the reds, pin 87A, always has ground because it's directly hooked up to this ground terminal. Now, the default position of a Bosch style relay is connecting pin 30 to pin 87A. So that is the blue wire to the red wire. So that means both of these blue wires are connected to these red wires right now with nothing turned on. And that means both of these blues are grounded. Now, when we push one of these buttons, what it's doing is it is turning on one of these relays. And by doing so, it's connecting pin 30 to pin 87. Now, pin 87 is the yellow wire, so that means that one of the relays is sending power from yellow to blue, which is turning on one of these red and black wires. Now, if we click the other button, we're actually reversing the polarity because the other relay is default to ground, and then we're turning the opposite relay on, which is sending power out the opposite terminal and reversing the power window motor. Now, you might be asking, what happens if you turn on both wires at once? And right now we can't because they're set up to be momentary. But if we switch it like this, and we take off the momentary, now we could technically turn on both of these powers at once. Let's do it. You'll see it does nothing. And that's because we lost the ground to the motor. And that means both the red and the black going to the motor are power wires. So now without a ground, the motor does nothing. But if we turn off one button, we get the ground back because the relay turns off and the window motor starts up again. Now, if window motors aren't your thing, but door lock actuators are, they are actually wired exactly the same. We just reverse the polarity on the door lock actuator, just like we did with the power window motor, and you'll see it does the same exact thing that the power window motor does. It just goes in and out instead of, spinning left and spinning right. Now, the starter itself is actually an interesting beast because we have to swap the negative trigger wire to be a positive trigger wire, and that's totally possible to do with the help of a relay. Now, a starter is actually really easy to wire because it only needs 2 wires going to it. You'll notice I have 3, and that's because I can't ground my starter to a wooden workbench. So I need to add this big fat ground wire to it to make it work for this demonstration. But you're not going to have this big ground wire going to it. Your starter grounds right through your engine block or possibly your transmission. Now, the power wire for the starter comes right from the battery and it goes to the starter solenoid. It's this big red fat wire. And then the solenoid just needs to be told when to turn on and off, which is done by this yellow wire. Normally, this yellow wire goes right to your ignition switch, so when you turn on the ignition switch and you go to the start position, it sends power to the starter solenoid, and then the starter turns on, something like this. But in this case, where this fuse panel and this switch panel is actually telling the ground wire to turn on and off, we need to swap this to make it a positive wire instead of a negative wire. Up here in the corner, you'll notice that I have the colors of the wires corresponding to the pins on this Bosch style relay, and your wire colors might be different, but I just wanted to explain what these wires and pins are going to. So you'll notice that the black wire is pin 85, the yellow wire is pin 87, the white wire is pin 86, and the blue wire is pin 30. Now the actual terminal that is telling the solenoid to turn on and off through this relay actually doesn't have a lot of amperage going through it. The big amperage for the starter is through this big fat power wire that goes through your battery. Now this starter is from a Mitsubishi, and I don't know exactly which one, but I can tell you that it draws between 5 and 10 amps through this circuit to turn on the starter, and it's currently connected to a 30 amp fuse. So I can actually downsize that to be a little safer, and I could put a 10 amp fuse in its place, and it should work perfectly fine. Let's test it out. All right, so now because this draws more than 5 amps, if I was to put a 5 amp fuse in this place, it would pop the 5 amp fuse. But if I do a 30 amp fuse, that's actually giving me 20 extra amps of like space, which it doesn't really need. I would much rather have it pop at 10 amps if something goes wrong than have potentially 30 amps going through it, which is just, overboard. Now the actual wiring of the relay is actually quite easy. You can see the yellow wire here is pin 87 on the relay. The blue wire is pin 30, and that gets tied in to pin 86. So the blue and the white wire are actually connected together right here, and then they both go into the positive terminal on this fuse panel. Pin 85 is the black wire, and that comes down here and gets connected to the negative terminal on this fuse panel. Now when we push this button, this board is going to give this negative wire a ground, and that is going to come over here and turn on the relay. And when the relay is turned on, it connects pin 30 to 87. And as you know, pin 30 is the blue wire, which goes to positive. So that means we are going to connect the positive blue to the yellow, which is pin 87, which is then going to turn our starter on. Now the fuel pump is actually really easy to wire, and you would just send both wires all the way back to the fuse panel. However, that is different than many fuel pump circuits because a lot of the time a fuel pump is actually turned on with the power wire, not the ground wire. So this ground wire goes back and it turns on and off depending on how you push the buttons, and the power actually has power all the time, which you can see here if I put the meter on it. So you can see the switches are all turned off completely, but there's still power going to this. However, you'll see that there's no ground. So if I go like this, we got nothing. And that's because the ground is turned off by this fuse panel, and by the switch, of course. Now you have to know how many amps your fuel pump is drawing to make sure that you put the wires in the right spot. You'll see that these wires go to the 30 amp spot on the fuse panel. But the fun fact about this fuel pump is it only draws 18 amps at its maximum flow. So I could actually just take this 30 amp fuse right out, and I could put a 20 in its place. You can always downsize the circuit, but you can never go up. So if this is a 30 amp circuit, then, which it says right here on the sides, you could always go to 20 or 10 or 5, but you can never put a 40 amp fuse in here or you're going to burn out the whole circuit, which would not only burn out your fuse panel and your new switch, but it might actually light everything on fire, which is not ideal. This is a little bit of a different design than many cars are wired with. Normally, the power wire is turned on and off for a fuel pump, and the ground exists all the time. So the ground usually goes right to a chassis, and then the power wire goes back to a relay, which is then turned on and off. Now that doesn't make this method bad, it's just a different way of wiring. So it's something that you just need to understand when you're wiring a fuel pump or really any accessory. Now this means that I can't wire this fuel pump into one of these smaller slots here with like the 10 amp fuses, because if I have a 10 amp circuit and my fuel pump is drawing 18, then I'm going to obviously pop the fuse and, the fuel pump's not going to run. And even if I went to 15, I'd probably pop the 15 amp fuse as well. But if I go up to the 20 or the 30 amp spots, that's going to be totally fine because the fuel pump only draws 18 at the max. Now I did mention earlier in the video that I might hook up a fan, and that's exactly what I'm doing. So we're turning on the circuit breaker. We have the fan wired into this 30 amp fuse spot. We'll turn on the switch and maybe set it up to a fun color. Maybe turn down the brightness a little bit. Nah, we'll go full brightness. Let's go for it. All right, so now if we push this button, it's going to turn on this circuit and turn on the fan. But it doesn't end there. Now you'll notice that this cooling fan is a 12-volt fan, and it draws 80 watts. Typically, a car, when the alternator is running, you actually get more than 12 volts. You get between 12 and 13.5 volts if all things are working properly. 12 is actually on the very low end. So generally when your car is running, you have about 13.5 volts. So to figure out the amp size that this circuit should need, you do 80 watts divided by 13.5 volts, because that's what your alternator is putting out, and you get 5.92 amps. So this fan is drawing 5.92 amps, depending on this voltage right here. It could waver just a little bit. And you can see I have it set up for a 30 amp fuse, so that's obviously way too much. So I can actually remove this 30 amp fuse, and I can put a 10 amp fuse in its place. Now I could actually go for a 7.5 amp fuse if I had one of those, but I'm going to go with a 10 because I don't have a 7.5 on hand. Ideally, I'd want to go with a 7.5 because typically fuse sizes go in 2.5 amp increments. So if you could find a 7.5 in this instance, I'd probably go with that. Now I only have a 10 handy at the moment, so I'm going to go with a 10, and now we're going to see if it turns on. And it does. Now wiring up a fan to a switch is a little bit boring, so let's actually measure the amperage that's actually being drawn by this fan. And we'll talk about what happens when the fan turns on versus what happens when the fan is actually running. Now this magical little device here will tell us the voltage and the amperage that are flowing through this blue wire when the fan is turned on, and it does that with induction. So let's turn this on, and you'll see I am at 13.8 volts, which is pretty great for my battery. It means I'm fully charged, all is well. And then you can see the amperage is 0 because there's no amperage flowing through the blue wire at the moment. Now, whenever you start up an electric motor, just like this one, it draws a lot of amperage at the very beginning when it's first starting up. And then when it's spinning at its normal rate, it's actually a much lower amperage. So when we first start this, we're going to see the amperage go really high for just maybe a second or two, and then it's going to level out and be right around our 5.92 amps. So let's see if I'm right. Now, when the fan first started, you saw this thing drop to about 13.1 volts, and it went to, I think it was around 10 amps or maybe just above. And then once it settled down and it got into its normal rhythm, we were at about 5.1 amps or something like that. We redid the math, and we took 80 watts divided by 13.1 volts, because that's what was actually showing on this meter, and we get 6.1 amps is what it should have been drawing, but this told us it was about 5.1. Now, why would that be? Well, it could be a couple different reasons. Maybe the fan is not actually drawing 80 watts. Maybe it's a little bit of a different number. Maybe this gauge that cost me a whopping $17 is not as accurate as I would like. But if nothing else, at least we learned how to actually figure out the amperage size for whatever component you're installing on your vehicle. You just take your wattage, divide it by your voltage, and you get your amperage. And that should give you a good ballpark estimate of what size fuse to use. Now, one other thing I wanted to try is what if we hooked up the fan to the flasher circuit of this CoLight switch? Let's do it. So we'll turn it on. We'll get to the red flashing part, switch it to the blue, click on the fan switch, turn it off, and then, actually, let's turn this on so we can watch the amperage and the voltage. And now, okay, that's fun. Now, what if we make it a momentary switch instead? Let's do that. So we'll turn it on. We'll go to this, the red flashing, click the button, turn it off. We'll turn on our gauge here, and then Okay, one more thing. I just have to see if I can blow a fuse here. What I'm going to do is I'm going to pull out the 10 amp. I'm going to put in a 5 amp. And then I'm going to use the momentary switch to keep the amperage really high as it's being drawn through the fan at startup. So I'm going to try and keep the fan in a startup mode so that it pulls as much amperage through the fuse as possible and tries to blow the fuse. Okay, so that didn't pop the fuse, and I think I know why, but I'm not 100% sure. Maybe you can leave me some notes in the comment and let me know what you think. But my theory is that fuses take a little bit of time to actually pop. So they can handle a little bit over the amount that's rated on them for a very small amount of time. And I think that we didn't go over 5 amps for a long enough time to actually blow the fuse. I think if we could get 6 amps for more than like a second or two, I think that we could probably pop the fuse. But since we couldn't seem to do that, it was like going above and below 6 amps very quickly. I think it just wasn't enough to pop the fuse. If I had a 2.5 amp or a 3 amp, I'd do it for sure. But the 5 amp is right on that cusp where it's just not going to blow. Now, you know I'm not a quitter when it comes to blowing fuses, so what we're going to do next is we are actually going to just jam a screwdriver into the fan and prevent the fan from starting up. And when that happens, the motor is going to draw a lot of amperage, and it's going to blow this 5 amp fuse. Let's see if I'm right. So we've turned it on, and now let's turn on the gauge. We have our voltage and amperage. Here we go. There we go. Now we've blown the fuse. I don't know if you guys just saw that. Maybe I can show a close-up of it. So this is actually crazy, and I've never seen this before. This fuse failed in a way that actually kept it going. So it's actually a failed fuse. So this is actually pretty exciting. I've never seen this happen before, and I now have it on film. You can see there's 8 amps being drawn through this wire, trying to make the fan go. Ooh, yikes. Don't do that. There we go. But the fuse is still working even though it popped. Let's get a close-up of the fuse. So now if you look at the fuse, you can see that it's burned down toward the bottom, but the actual part that burns flipped up, and it's actually making the connection across both of these terminals again. So the fuse failed, but it failed in a way that actually made the fuse work again. I've actually never seen this, and this is actually kind of fascinating to me. Here's a comparison of what it should look like compared to what exactly happened to it. So you can see the one on the right has the S-shaped fuse, or filament, or whatever you want to call it, in the middle. And the one on the left is the one that burned, but actually reconnected itself. We now have a new 5 amp fuse in this fuse spot, and we're going to try and pop it for real without it somehow coming back to life again. So let's turn on the fan, we'll jam the screwdriver in it again, and we will see what happens this second time. Okay, we've got our meter turned on. We're only at 12.7 volts, which is not as much as we were at before. So we might have to redo our math again and see how much amps we're technically pulling, but we should be able to read it on the gauge. 9 amps. There's 9 amps apparently going through this 5 amp fuse, and it's not blowing. That's pretty disappointing as far as fuses go, because I would want my 5 amps to pop. And there it went. It looks like our 9 amps can go through our 5 amp fuse for quite a few seconds before it actually pops. And now you can see we're down to 0 amps going through the blue wire because there's no more electricity passing through this fuse. So no matter whether the screwdriver's in or out, there's nothing happening with that fan anymore until we replace this fuse. And now here is the newly burned fuse. And you can see that there's no more connection between the left and the right terminal anymore, and there is no way electricity will ever pass through this fuse again. Now, if you want to see me wire up a fan to a temperature sensor, then go ahead and watch the next video that I'm going to put in the corner right here. And if you want to buy one of these switches, it is made by CoLight, and there will be a link in the description. Thank you so much for watching, and hopefully I will see you on the next one.